All right, welcome back again, everyone. Just looking at the video I just prepared for 30.1.1, which was the introduction to this unit covering momentum. It turned out to be about 23 minutes long, and again, these videos I'm preparing for the first three lessons are considerably quicker in pace than we covered in class. In class, that 23 minutes would have been at least double. So, just like with the previous video, for those of you that are trying to catch up because you were not in our course for the first 3 days, you're going to have to pause the video at times and keep up with things. Don't rush yourself. If you're writing really fast and furiously to copy down something I'm saying, or if I say something that triggers an idea that you want to put down on paper, pause the video at that point and copy down your thought before you forget it. This is the second lesson in the unit. This covers impulse. In this lesson, we defined impulse. We talked about what's necessary for impulse to happen, whatever impulse is, and we'll get to that. And then we calculated impulse using a variety of definitions. There's a fair amount in this unit. We also talked about how impulse and the concept of impulse can be used to explain safety devices. But then basically, we also put this all together into one tidy little formula, which is F delta T equals M delta V. Just kind of thinking ahead here, the quiz that you wrote on Friday, I believe the second question asks you to find a force acting on an object. You would probably use F delta T equals M delta V to answer that. A little bit later, of course, I will make a video of the solutions to those quiz problems. To begin with, we defined impulse. Impulse is defined as the change in an object's momentum. We need to be very cautious here because if impulse is the change in an object's momentum, then whatever the units are for impulse, that will be the units for momentum. And clearly, impulse and momentum are really closely connected, but they are not the same. Impulse is how much the momentum changes by from one point in time to the other, whereas momentum is simply how much momentum an object has at a specific point in time. Of course, change in is denoted with the delta symbol, the capital Greek delta letter, and it means final minus initial. So anytime we see this delta x equals final x minus initial x, what that means is that if you want to find impulse, and this is something that we talked about a little bit in class, and I need to mention it here on the video as well. We do not have a special symbol for impulse in high school physics. There is a symbol that's used, but I'd rather not even talk about what it is because it can cause confusion. If you want to write out symbols for impulse, you write delta p with a vector above it. But since delta means final minus initial, impulse is final momentum minus initial momentum. Well, we know how to calculate momentum. It's mass times velocity. So impulse can also be found using mvf minus mvi. Of course, vectors are important. But I can factor, mathematically speaking, I can factor an m out of those two terms and be left with vf minus vi. And that means, since final velocity minus initial velocity is change in velocity, m delta v is how we can calculate impulse. Number one, determine the impulse experience in each of the following cases. A 1,500 kilogram sports car accelerates from 10 to 35 meters per second. So just like the last video, there are going to be problems here where I don't show all of my work. However, for this one, I would like to show all of my work, with the exception of writing down units. We have the mass, which is in kilograms. We have VI and VF, which are both in meters per second, so we don't need to worry about anything weird here in terms of converting units. Now, I'm not actually told the direction the car is traveling in, but it is always traveling in the same direction. I mean, if I say that the initial velocity is positive 10 meters per second, then the implication in this question is that it's traveling at positive 35 meters per second. There's nothing in this question that says the car changes direction. So all we're going to do is we're going to take the mass of 1,500 kilograms and multiply by the final velocity minus the initial velocity. Once again, I just leave out, when I'm teaching, I just leave out the units, and you can leave them out when you're solving problems, because I think it makes it cleaner and easier to get answers. And I know many teachers would disagree with that, but that's fine. If it is a written response question, then certainly you're going to put the units, and there will be a time where we do need to look at units in detail, but not in a question like this. They'll just get in the way. So all we have to do is multiply this out. What do I get? 1,500 times 25. 35 minus 10 is 25. I'm getting 3,750, or I suppose 3.8 times 10 to the 3 kilogram meter per second. I don't care if you write 3,750 kilogram meter per second. B. Now, quiz question number 1 was basically this question. And we talked about this in class numerous times. If you want to find the impulse experienced by an object in this situation, since impulse is change in momentum, and momentum is a vector, we need to be very cautious about the numbers we put in for the initial and final velocities. You have a ball traveling towards the floor, and in the instant before the ball touches the floor on its way down, it's moving with a speed of 5 meters per second. I'm going to draw the ball rebounding over to the right. Of course, the ball doesn't magically appear on the right. I'm just drawing it over here. Afterwards, as soon as it leaves the floor, it's traveling up at 3.5 meters per second. Well, these are the speeds. You're told these are the speeds in the question. But if you want to talk about velocity, the velocity initially is negative 5 because it's moving down. The velocity afterwards is positive 3.5. It's a little cluttered. Let me just clean this up a bit so that you can see that a little better. And that changes everything. If you don't include that negative with the 5 meters per second, you will get the question wrong. So we are going to have, well, I'll write this as m delta v, which is m times vf minus vi, which is going to be the 0.5 kilograms times positive 3.5 minus that negative 5. And if you don't include that negative, you will get the wrong answer, both in this question and on the quiz that you wrote. So 0.5 multiplied by, well, in brackets, it's going to be 8.5. You can use your calculator for that part. But I get 4.25 kilogram meter per second. And right now, you and I are strictly speaking in teaching and learning mode. I don't care about significant figures here at all. It's not important with what we're dealing with. We want to learn the physics. Now, this next bit of business is fairly important. And I spent a lot more time in class than I'm going to here with it. So you're going to have to think about this. If a mass experiences an impulse, then by definition, it has to have a change in momentum. And the only way for the momentum to change is if the velocity changes, because momentum is connected to velocity. In Physics 20, in Science 10, and in Physics 30, we are expected to know that a changing velocity is an acceleration. But we are also expected to know, and this is more from Physics 20 than Science 10, that the only way you can get an object to accelerate is to have a net unbalanced force acting on the mass. That means that there must be a connection between the impulse experienced and the force acting, the net force acting on it. What I'm saying is the net force produces an acceleration That acceleration produces a change in velocity. A change in velocity, by definition, is a change in momentum, and that's what impulse is. I'm saying there's got to be a connection between net force and impulse, and here it is. The net force is equal to ma, and acceleration is equal to change in velocity over change in time. All I'm going to do, everyone, is take this and put it in there because that's what acceleration is. So rather than having ma, I'm going to have m times delta v over delta t. And if I multiply both sides by delta t, I get this thing, which connects everything together. What this is a marriage of dynamics, F equals ma, and kinematics, A equals delta V over delta T. This is on your formula sheet, but it does not have the net as a subscript. One of the things we need to remember, there it is on your formula sheet, one of the things we need to remember is that m delta V is impulse, but if you look at that formula, m delta V equals F delta T, so F delta T is also impulse. We have a new way to calculate impulse. It's F delta T. In this formula, m delta V is impulse, but it's equal to F delta T, so F delta T is impulse. This is what I'm telling you. Example number 2, a 12 kilogram ball is dropped and takes 1.2 seconds to reach the ground. What is the magnitude of the impulse? Well, we can use F delta T. And we're asked for the magnitude, so I suppose I don't really need to worry about the force. Now, I could just take the force times the time and show you how to get it, but this is kind of tricky because it says, what is the impulse when the ball hits the ground and stops? You need to appreciate that however much momentum the ball gains in the time it takes to reach the floor, in other words, however much momentum it gains in falling, magnitude-wise, has to be exactly the same as the amount of momentum, magnitude-wise, that it loses when the floor stops it. So what I'm going to do instead is calculate the magnitude of the impulse as it falls. And as the bowling ball is falling, this is the bowling ball, there are the finger holes. As the bowling ball is falling, there is only one force acting on it, and that's the force due to gravity, which can be found by taking m times g, 9.81 newtons per kilogram downward, or meters per second squared downward. Bottom line is the magnitude of the force. This is impulse. This is change in momentum. Well, it's the magnitude of the change in the momentum. Well, I'm not using vectors here because I'm not asked to. This will be m times g times t. I don't like to use delta t there. This is a very simple question once you set it up that way. The mass of the bowling ball is 12 kilograms. I don't bowl. That seems like an awfully heavy bowling ball, but let's just assume that it's right. Multiplied by 9.81, multiplied by 1.6. So what we're getting for an answer is 188. And this introduces now the fact that we can write units for impulse and momentum. Instead of saying kilogram meter per second, we can use Newton seconds. Very briefly. In class, we had about a 10-minute discussion as to why a Newton multiplied by a second is a kilogram multiplied by a meter per second squared. I'm not going to explain that here. Take my word for it, and we will discuss this. It's going to come up again later in the unit and the course, that this set of units is exactly the same as this set of units. So that's the answer to number 2. Number 3, a large truck has a momentum of 400,000 kilogram meter per second. It says use equivalent units to explain what this means. Well, I'm going to use the equivalent units of Newton seconds. What this means is that if I wanted to stop the truck and it has this much momentum, the product of the magnitude of the force and the time has to be 400,000 Newton seconds. Or, in order to get the truck to have that momentum from rest, you would have to apply a force over a time interval, and the product of the force and the time have to be 400,000 Newton seconds. In terms of stopping the truck, I can use a net force of 4,000 newtons with a time to stop the truck of 100 seconds. The bottom line is I can use any force I want, in theory. The time just has to be a time that when the force and the time are multiplied, you get 400,000. I mean, I suppose you could instead use a stopping force of 400 newtons, which means you're not applying as great a force on the brake pedal, or maybe there's a little bit of slipperiness to the road, I don't know. But you're going to have a stopping time of 1,000 seconds. And you can pick any two numbers that multiply to give 400,000. That's the meaning of saying Newton seconds. That leads us to a very important idea regarding safety devices. If you have an object that is going to be stopped, we'll get to this question in a second. If you have an object that is going to be stopped, then you can apply a very large force, and what will happen is it will stop very quickly. I mean, I can go back to this one. We used a force of 4,000 newtons, and it only took 100 seconds to stop. If I use a smaller force, then what happens is it takes longer to stop. When we start talking about things like airbags that prevent serious injuries in car crashes, or bungee cords which slow you down to a stop when you bungee jump, or the example I use in class is if I stand on a chair and I jump off of the chair, when I hit the floor, it's a very wise decision for me to start bending my knees as I hit the floor. All of these things, and I'm not going to write much down here. You can pause the video wherever you like and write down whatever you think you need to. All of these situations take the time it takes to stop and increase the time, reducing the force. So, for example, if I have a very large average net force stopping somebody in a collision, maybe this is just a seat belt. When that seat belt stops you, because the seat belt is kind of unforgiving, it produces a large force, and you're stopped in a very short period of time. If you have an airbag, what happens is you have a smaller average force, and it takes longer to stop, which is a good thing. So it reduces the injury. If I were to jump off of a chair and land with my knees locked, we could have a conversation about what happens after somebody phones an ambulance for me, but the conversation would involve I was an idiot because I was stopping myself in a very, very tiny period of time, which produced an incredible force on my knees. Number 5, an 85-gram ball hits the floor with a velocity of 2.2 meters per second and bounces up at 1.3. There is a bit of a lie in that first sentence, and this isn't a mistake on my part. This happens on exams from time to time. You'll see this. If the velocity is 2.2 meters per second and it hits the floor with that, we need to know that that is a negative velocity. It's 2.2 meters per second down. The collision between the ball and the floor occurs over 0.22 seconds. What's the force on the ball? Well, if this were physics 20, everybody, you would have to use F equals ma to find an acceleration. F net equals ma to find an acceleration. And then use kinematics to find the time, or vice versa. I guess in this case you would use kinematics to find an acceleration, and then use F net equals ma to find the force. The bottom line is these types of problems we see in Physics 30 involve kinematics and dynamics, but we have that formula, which is the marriage between dynamics, F delta T, and kinematics, M delta V. So when you see this type of question, like quiz question 2 on the quiz you wrote, we can just go ahead and put in all of the information. This is 0.22 seconds. The mass is 0.085. Vf minus Vi, of course, is what we use for delta V. Vf is positive 1.3 minus Vi is negative 2.2. It's simply a matter of grabbing our calculator and taking care of business. Let's see, 0.085 multiplied by, that will be 3.5 in the brackets. And then divided by that 0.22 gives me a force of about 1.4 newtons. And I'm getting a positive force, which means it's 1.4 newtons up, which makes sense. The force on the ball is up. That explains why the ball goes from moving down to moving up. One final example, I believe, in this lesson. A satellite has a particular mass. The average net force of the thruster rocket is 150 newtons. The rocket needs to change its velocity by 3.5 meters per second. So this is neither Vi nor Vf, it's delta V. How long should the thruster be fired? Very basic question, F delta T equals M delta V. F is 150 newtons. The time is what we're after. The mass is 1,800 kilograms. And the change in the velocity is 3.5 meters per second. We're in the realm of stealing candy from a baby at this point. It's just 1,800 times 3.5 divided by 150 gives me 42 seconds. So the thrusters need to be fired for 42 seconds. And I believe that takes us, that takes us to the end of lesson 1.2. Again, went through a lot quicker than I would have in class. I didn't keep track of the clock here, but I suspect whatever time this took, maybe 25 minutes or so, double that. That's the depth we went to in class. I have one more video to do with regards to the lessons. I will get to work on that right away. That will be the one where we talk about area, graphs, force, and time, and how they are all connected to each other. I hope that helps.